Hey everyone, I've decided to start a new series on this channel. And this will be dedicated to solving programming problems, specifically in Rust. Why Rust, you may ask? It's a really great language. I've started dabbling in Rust since the past few months, and it has slowly turned out to be one of my favorite programming languages. I don't intend to make this a tutorial in Rust. I'm by no means a Rust expert, but I shall just solve problems, as in the spirit of this channel, we try to learn new concepts by doing. So we try to solve problems and we learn the essentials that are needed to solve a particular problem. So in today's video, we'll be trying to solve the n queens problem. I've opened LeetCode here. It's an online judge that I often use. It's quite convenient. The interface is quite nice, but if you guys have any other suggestions for other online judges that you use, yeah, please let me know. Yeah, so the n queens problem has been quite famous for decades even. It has occurred on programming tests, interview questions. It's a nice problem to start off when you're learning algorithms, trying to learn new concepts such as backtracking. So the problem is given an n by n chessboard. In this case, you see a 4x4 chessboard. We need to place n queens such that no queen attacks any other queen. Okay. And in this particular problem, we are to output the entire board configuration, like you can see here, row-wise. So in chess terms, the horizontal rows are called ranks. So essentially, we need to output the positions of the queens along the ranks in all of the possible configurations. So for a board of 4, we have 2 distinct configurations, as you can see. Yeah, that's it. The constraints are we need to solve this problem for a board configuration of any n from 1 to 9. Yeah, so the largest chessboard can be 9 by 9. Right, so here on the right side, I've selected Rust, and this gives me the generic input block. I tend to like programming locally, so I will copy this move over to the terminal. I have a directory, LeetCode here, and how you start this is already great. So how you start a Rust project, in our specific case, we'll start a Rust binary, is by typing in the command cargo. I would assume that you guys would have Rust installed on your system. If not, please look at the instructions online. Yeah, once you have Rust installed, you start with cargo new --bin for binary. And let's call our binary n queens. Great, so we have our binary created. Let's head over to the directory. Right, we're gonna open this in VS Code now. So what you see here is a cargo.toml file. This cargo is essentially the build system as well as the package manager bundled into one. It's very convenient. It's also a dependency manager. So all your dependencies for your binary go in here, and a few other specifications. Then all the source code in a Rust project has to lie within the source directory. And every binary should have a main.rs file. And the first function that is called when you run the binary is the main function within the main.rs file. So if we open a terminal here, this code is basically the scaffolding code that comes up when you run cargo new. So to run the program, you do a cargo run, it prints hello world. All right, so we go back, we copy our code, and I'm gonna paste it here. I've set up the Rust analyzer. It's quite helpful when you're programming in Rust in VS Code. It shows you all the errors, because right now we're not returning anything, but anyways, we will get to that. So this is our function. It takes as an input, it's an i32 type of the size of our chessboard, and then it should return a vector of strings. That's basically the queen configurations rank-wise. Right, so how do we approach this problem? There are several approaches to solving this. You might have heard about backtracking solutions. Then there are these other innovative solutions where queens are placed randomly across the chessboard and then the conflicting positions are resolved. But what we are going to see today is a very sort of brute force approach. What we're going to do is we will look at each rank. For example, the first rank here it's 4 by 4, and we try to place a queen such that the configuration is valid. So initially you might think, if you want to place a queen, just one queen on 4 squares for this 4 by 4 chessboard, you should be able to place it on any of the squares because there is no other queen. And that gives us the first set of solutions. That's basically the 4 solutions. And then we incrementally add to each of these solutions. So for the first solution, let's assume that the queen is on the top left square. And then trying to build on that solution, we can see that for the second row, we can't place a queen on the first and second squares, but we can place a queen on the third and fourth squares. So those two then build up on the initial solution. And then for every square, we incrementally add a rank and add a new queen. And at the end, once we're done with all of the ranks, we should be done with our solution. So we'll get all of the valid configurations. So it's like a brute force approach. So that's what we're going to code up, and let's start. Right, so I will define another function, which will just, I'll call it generate. It's not a great name, but we'll go with that. We'll have a current set of configurations that we shall work with. It's going to be a vector of I32. Now, this is basically an index of the queen on the chessboard. As we see, we are dealing with a 2D grid here, but there is a method by which you can convert any 2D index to a 1D index. For example, if you start from the top, it's 0, 0, 0, 1, 0, 2, 0, 3, and then 1, 0, 1, 1, and so on. And this you can convert to a 1D index, which means the row will be 0, 1, 2, 3, and then the second row will be 4, 5, 6, 7, and so on. The technique to do this is very simple. Let's define these two functions. Square to index, which takes in a 2D grid cell and then converts it into a 1D. And here what you do is, well, you also need n, because you need to know how many rows and columns there are. You could do this for a m by n grid. In our case, it's a square grid, but this even works for rectangular grids. Anyway, so the answer here is nx plus y. So here you can see if x is 0, 1 and n is 4, you will get an index of 0, which is correct. For 0, 2, you will get an index of 2, and so on. For 1, 0, you would get an index of 4, which is basically the next rank, right? An equivalent function we can write is index2 square, which takes in an index and n, of course, and then returns a tuple. Tuples are indicated by parentheses in Rust, and this would be index divided by n, and index mod of n. Right, so y is the remainder, and x is the integral division. And now our functions are there, so we can efficiently convert between 2D grid points and 1D grid points. So coming back to our generate function, this will take in an incremental list of solutions that's current. Let's also take in n. And when the size of current is equal to n, which means we have constructed solutions for all of the ranks, the solutions that are returned would be the final solutions. Right, this would be our signature for now. Right, I can explain about references. So what we are passing here with the and sign, it's a reference to a vector of a vector, and this is a immutable reference, so current cannot change. So we'll construct the new set of solutions and we'll return them. Okay, so let's write the formula for every solution. All right, now we need to check if a queen attacks any other queen in a configuration. So let's write this function, solution, and this will be a configuration of I32, and it will return a boolean. It'll return true if the configuration is correct and the queens are not attacking each other, and false otherwise. So we'll have to check each queen with each other queen. We'll use an index. this is how for loops are written in Rust. So we'll check for the ith queen with the jth queen, and this will run from -1. We have to extract the square in which the ith queen sits. So we will have to call index to square, and that's right. And square 2 let's just do it false here. You see that I'm not using the return keyword. This is because Rust does not require the use of the return keyword in terminating expression. So if you don't use the semicolon at the end, it is implicitly assumed that we are returning the value of the expression. Right, I'm missing the n here. Okay, so we have the two squares. How do we determine that the two squares are not attacking each other? The first thing is that the rows and the columns, so the ranks and the files, should not be the same. So if square 1 and the first element of the tuple is given by 0 and the second is 1 and so on, if the ranks are the same or the columns are the same, then this should be true. We will handle the attacking cases here. We return false. And now let's think about the diagonal attacks. If we go back to the figure, so if you were to take two squares which are diagonally connected to each other, you will see that the difference in x, or the difference in the files, is equal to the difference in the ranks. So we can use that fact and write this code. So if square 1 dot 0, so that's the difference in the ranks, and we have to take the absolute value of this, is equal, let's copy this, to the absolute value difference in the files, then these squares also lie diagonally. So this function now will return true if the solution has a valid configuration of queens, otherwise it'll return false. Right, so now let's build our current set of solutions. We will look at the current rank. That's how many ranks we have solved until now, and that's basically the solution. Now we'll go for the files. So file in, we'll try to place a queen on the next rank on every file. So we go from 0 to n, and we will copy the current solution. This is how mutable variables are defined. So we make a copy of the current solution. Again, let me define a return, which is, let's say return, that's fine, same type. And we define it like this, return it. Okay. If you go to the Rust-Lang book, you can read more about variables and mutability 3.1. Essentially, all variables are immutable by default, and if you have to define mutable variables, you have to explicitly state the keyword mute. Okay, right. So for every new queen, we have a new mutable variable, solution new, which clones our original solution and tries to add a new queen on the new position given by file. Okay, so we add this queen. So vector pushback in C++ is push in Rust. We use our square to index function. So x here is the new rank, so rank plus 1. Y is the file this is correct, we add this solution to the solutions. Okay, I have to use self here, which is why is it complaining? Missing n. Right. So if the new solution, so the new queen position, does not disturb the earlier configuration, we add it to the new list of solutions. And that's it. Let's try to call this for n from our function. Let solutions. We'll construct the strings in a moment, but let's call generate. So generate will be called n times, and every time this has to be mutable. Every time we call it, we'll save the new solution to our solutions vector. First, we need to populate the current solutions. That would be for I. This is basically the file in the first rank. So we can copy this. New solution, and this will just be a new vector. And obtus. Here, the rank will be 0. And actually, this can be done in this manner. Let's solve this for a moment. We are populating solutions with the initial position of every queen. So this is basically a vector with one element. That's the position of a queen on the given file. So if you go back, it's trying to place, so the initial configuration is one queen on each square of the first rank. Right, and now we have to run this for n times, where solutions will be given by generate. Self generate, and it will be called upon itself, and this will be called n times, and eventually we'll have a number of solutions. Okay, let's also write this down for the solution in solutions, and we should take a reference. Let's indicate this by solution string. That's the position of the queen. And we need the square here. We don't need the rank. We need the file. So this will be index to square of the position of the queen. This index is basically in solution. Right, now index is a reference to I32, so we will have to dereference it. So now we have the file. Let a string equal to, we have to write the file as a string, so we map this iterator. Let's say call it j, and if j is equal to file, we have a q, else we have a dot. Right, and now this has to be collected. And for every index, we need to save the string to substring. And the solve string would then be added to red. Cool. Let's try and call this function. Let's have equal to 4, and result is solution of n queens for n, and we'll try to print the result and see if you got it right. And queens configs will be given by so there's rest.length. So let's rest. I use this colon question mark syntax as this is used for non-standard types. Of course, non-standard types that implement a debug trait use this. Anyways, I won't go into details of the debug trait. If you're interested, please take a look at the Rustlang book. All right, so let's see if this builds. We have a few errors here. Right, this should be %. And here, what's the problem? Solve string, right, this is mutable. J isn't used. Oh, this should be J, my mistake. Should be fine then. Great, it compiles. Another thing I'd like to note is that you can always run cargo format. It's a standard formatter that formats Rust code in the same way everywhere, so it's pretty cool. Right, now to run code, let's run it. We have 0 configs. Let's see what went wrong here. Let's print the solutions. Solutions are being printed correctly. So I found the issue. The issue was very funny. So essentially, when we reach the end, the last rank, we don't have any more people to add. So the final solution is empty. So the problem is we should not run it for n times. We should only run it for n-1 times. And this should fix our issue. Right, 4 queens have 2 configs. Let's test for 1 queen. 1 config is correct. 2 queens cannot be placed in a 2x2 chessboard, so this should be 0. Interesting. Returns 2. That should not be the case. Somehow our logic seems to be wrong. Absolute value. So this configuration is also wrong. I found the problem. Rank is the length, which means in 0 index, it should not be rank +1, but just rank. That was the issue. Let's see. Now, for 2 queens, we get 0. That's correct. Let's check for 1 again. Should be 1. For 3, it's also impossible to have 3 queens in a 3x3 chessboard. There should also be 0. For 4, should have 2 configs. This seems to be consistent with our solution. Alright, and let's check for 9. And that's 352. And I know that this is correct because there is a list online that shows solutions for all configurations. You can check it out. Yeah, so 9 queens have 352 solutions. Right, so we have solved it. Let's submit our solution. Right, looks good. I would try to run the test case just to make sure this is correct, and let's submit. Right, and this is accepted. If you look at the runtime, it's not that great. 11 percentile. Memory is 22 percentile. So yeah, there's a lot of optimizations that we can do, and I leave this as an exercise for you guys. I can also provide some hints here. So if you go back to this Wikipedia article, you see this thing called fundamental solutions and all solutions. So what are fundamental solutions? If you go back to our problem description, you see that both of the solutions are mirrored along the central line here. So they are vertically mirrored. And fundamental solutions are those solutions which are unique even when you mirror the solution vertically and horizontally, as well as rotate the configuration. So if you rotate it, you will also get some valid configurations. For example, if this one is rotated clockwise or anti-clockwise, you get the same result. So the solution is rotationally symmetric, so is this one. So they're distinct, but certain solutions are not rotationally symmetric, and they're also distinct solutions. So there is a way by which we can cut down the runtime by only working to figure out the fundamental solutions, and then we can rotate and reflect the solutions to get all of the unique solutions. So I leave that as an exercise. There are more things that possibly can be done. I mean, as you saw, this is quite a brute force approach. There is a backtracking approach as well, which you can take a look. But yeah, this is my take on the n-queens problem. I hope you enjoyed the video. If you did, please like and subscribe to my channel. It really helps out. And if you want me to continue the series, please let me know your suggestions. If there is any particular problem that you'd like me to show, as well as feel free to be a member on my Patreon. You can find the links in the description as well as in the About page. Well, that's it. Thanks again, and see you in the next one.